Welcome to Breadboarding. In the previous video, we managed to get our modern surface mount UART serial communications chip soldered onto a 48-pin DIP adapter here, and we wired it all up, and we're now in a position to sort the software out and start testing it. So this is video 7 in the Breadboard PC 8088 version 2 series, and this video we're going to be covering the serial port software and testing it. So almost got to the end of the first phase of our high-level plan. So this is building out our NanoComp 8088. So this is a simple computer using an LED display and keypad, running the NanoComp monitor, which has been migrated from the original 6809 monitor from the project a number of years ago. And in this video, we're going to be getting the serial port software to save and load data to the computer memory in the SREC file format. So SREC is a file format that allows binary data to be transferred up and down over serial type connections and includes a certain amount of error checking in it. And this will enable us then to have a platform that we can then build out the basic floppy disk PC and gives us something to do the test software and to check out all the hardware here as we're building it. And then we'll move on to add a hard disk, mouse, and extend the CGA video controller to all modes, including graphics mode. And we should then be able to run Windows 1, 2, and 3 like we did in the first series. So let's take a look at the datasheet first of all. We did cover some of the details in here in the previous video, but what I'm going to do now is to look at the registers that we need to worry about for configuring and programming this. So you'll see here that we have 3 address lines that gives us a possible 8 register options, but because we also have this DLAB bit for the divisor latch bit here that allows us to access divisor latch least significant byte and the divisor latch most significant byte, depending on if that bit is set in the line control register. So effectively gives us access to 10 registers, even though we're only using 8 addresses from our 3 address lines here. So one of the reasons why this has been delayed a little is I had some problems with it trying to get it working, and what I later find out is there was some interference on the master reset line that was actually resetting the status of the UART every probably some 2,000 times a second. So it might be able to send one character, but then the next characters would all then get messed up. So once I worked out what that problem was, then I've managed to make progress since then. And this table here really is probably the most useful. It summarizes what each of the registers is, and there's an acronym that is used throughout the software and throughout the documentation. And you can see here that the receive buffer register, where we receive the data from the PC, the transmitter where we put the data to send to the PC, and you can see that when the DLAB bit is 0, then this is used for sending and receiving data, and the interrupt enable register is also enabled when this bit is 0. However, when the bit is set to 1, which is actually set in the line status control register, you'll see here the divisor latch access bit is set here. When that is set, then we can then access the divisor least significant byte and most significant byte to enable the baud rate that we want. So we're going through these registers. There's a special register here for the 16550 series, which allows us to control the first in, first out 16-byte buffer configuration. By default, it's disabled, but if we write to this register, we can enable those facilities. The BIOS and the early versions of DOS didn't have support for this, so we won't be worrying about that. The line control register is probably the main one that we're going to be setting up the configuration, where we have the divisor latch access bit, plus also the word length and whether we want stop bits and no parity. The modem control register allows us to set the various modem control signals for doing hardware handshaking with the PC. The line status register allows us to check the current status for whether we've got data ready to read from the receive buffer and whether or not the transmitter holding register is empty and ready for another byte of data to be sent. The modem status register allows us to check the modem control lines, and there's a scratch register, which you'll see there's a bit of test code in there where I was testing out whether we were setting the correct bits and things in the data bus when I was having a few problems with the reset. And then we've got the divisor registers here, which we'll be setting to 12, which will give us a value of 9600 baud. So to help work out what software changes we need to make, I went into the BIOS, Sergei Kislev's XI8088 BIOS, and looked at the serial1.inc and serial2.inc, which is where all of the BIOS serial port communication services are. And so this includes most of the register definitions and the various bit values we need to worry about. So the transmitter holding register empty value and data ready, for example, are the two of the status values we need to worry about. And it's been useful to go through and look at what are the various values. So setting the data terminal ready and RTS when we're sending data, and when we're receiving data, we just set data terminal ready, for example. So I've summarized a lot of the information from there into this slide here. So basically, this is just a summary of the various bits and registers we need to worry about, and I've included this in the source code above each of the send and receive functions. So we don't need to go through this in detail here, but needless to say, we have to set this bit so we can set our port divisor for the speed that we want, initializing 8 bits, 1 stop bit, no parity, which is pretty much the standard for PCs after about the mid-80s. Going to disable interrupts, make sure we set the appropriate modem control signals. Then when we're receiving data, we need to check that the line status register, down here, we need to check that the data ready is set. That will indicate that there's some data available to read. When we read the receive buffer, then that bit will get cleared automatically. And then when we're sending data, before we write to the transmitting holding register, we need to check the line status register bit 4 to see whether or not the register is empty or not. So if we were to update this whilst it was still being sent, then you could overwrite the data that we're already in the process of sending. So we need to check these status bits before we receive or write data from the UART. The line control register has a couple of bits we need to worry about. So we're going to be setting bit 0 and bit 1 to a value of 3, which gives us 8-bit words. And then the stop bit value will be 0, which gives us 1 stop bit. And the problem I was having whilst I was testing this is that at random intervals, quite frequently, it's like 2,000 times a second, there was some interference on the reset line that would actually reset this back to 0. So we'd end up with 5 bits rather than 8 bits, which understandably messed things up in quite a big way. So let's take a look at the versions of the software. This is version 7, the new version on the left-hand side, and version 6, the version that we had in the previous video on the right-hand side. So I'm just going to go through the changes that we've made here. So you'll see over here that the original 6850 Motorola UART had 3 registers we needed to worry about, and this one has 10. So it's a bit more complicated. And we've also now got all of the various bit values that we need to worry about when talking to the various registers, in particular transmitter holding empty register and the data ready for the receive buffer. Then we've just updated the version to version 7, so we'll just check that we've got the right version when we start up the monitor. So this is the text that I showed you on the previous slide, so this has just been copied in and modified specific to receive. So most of the code here is to do with initialization of the UART. In the 6850 it was just really one register we need to configure, whereas this has quite a bit more. So we're setting up the baud rate, then setting the line control register, disable interrupts, and then we're also setting the data terminal ready and request to send modem control signals. And then we're into the rest of the code, which is pretty much unchanged until we get to the code which is actually talking to the serial port. So the receive byte is the bit that's talking to the serial port. So first of all, we actually have to check the modem status register to see whether we got the data set ready or the clear to send bits set. So either one of those will satisfy the test. It'll go around in that tight loop, waiting for one of those bits to be set. So this is the hardware flow control. Then once we've got one of those hardware flow control bits set, we then need to check that the ready bit is set. So the ready bit being 1 means we've got some data that's been received. And when we read the serial data buffer, then that will clear that bit. So we go around in that loop until such time as we've got some data, we read the data, and that will then clear that bit, and then we return the data. So then when we're going to send the data or save the data, we've got similar initialization. The only real difference is that the modem control register, we're only setting the data terminal ready in this particular case. You'll see there's quite a few bits here commented out where I was trying various things to see what the problem was. I was disabling the FIFO facilities explicitly, and you'll see there's quite a few of no operations and reading in values and things. And what I discovered is that the line control register is expected to be 3 the whole time, and at various points it was getting zeroed, which changed everything to 5 bits, which was going to mess things up big time. And you'll see as well that there's a test patterns I was using in the Scratch register, which is just a register available for general purpose testing. So I was just checking we were getting the right bit patterns coming through there. All that's been disabled now. And then I did come across a small bug in that when I was saving the data in a segment outside of the segment where the code was running from, it was using the wrong segment for sending the address. And so I've added a new facility, so send byte DSX, which uses a data segment and BX to send the data, whereas the default one uses the extra segment. So we've got another routine here, and the only difference between these two routines is that this one uses the data segment, this one uses the extra segment, and that just means that the address bytes will appear in the srecord file in the correct position. Then when we're sending, again, some debug code there expecting to look at the line control register, how I detected the problems. We need to check the data set ready and the clear to send bits. If one of those or one or both of those are set, then we know we can carry on. Otherwise, we just wait until such time as one of those is set. Then we need to test that the transmitter holding register is empty. If it isn't empty, we need to wait until such time as the data has been finished sending down the wire. Once it's empty, then we can actually send the data. And that's the changes. So all you need to do now is just to assemble that. The monitor is still part of the BIOS, so I'm just going to make the BIOS including the monitor, and then we're just going to program that into the EEPROM. Just read it to make sure it's in the right way. We just need to make sure that this is loaded 4K into the 32K EEPROM to allow for the IDE BIOS to be loaded at a later stage. So our BIOS should start from 100. Yep, goes down to the bottom, so we'll just program that. We'll put that back into the computer. Okay, so here we have the UART here. So this is our surface mount chip on the 48-pin DIP adapter. The 2 extra lines here, so the chip selects for the IO0XX range and the IO3XX range. I've missed out those. I have also added 2 extra links in here. So the problems I was talking about earlier to do with the interference on reset, what I'm now doing is taking the active low reset from here, feeding it into this side of the PLD and making use of an unused pin here to generate the active high reset, because this doesn't seem to have the same sort of problem. So most of the problems I've had causing delays were related to the interference on this, and I'll show you some captures from the oscilloscope to show how that has changed. Other than that, I think everything else should be the same. And you can see over here we've got a USB cable plugging into my laptop here into the USB serial converter. So just going to turn it on first of all, and we would expect to see the Nanocomp 8088 monitor version 7. That's good. So we've got version 7 coming up here. The voltage is a little bit below 5, but it's still within tolerance, so that should be okay. Now what I'm just going to do is to put the oscilloscope on the oscillator here. So just going to put that in first. So I'm just going to check that we've got 1.8 megahertz coming out of our oscillator here. We'll just switch over to the oscilloscope. There's the oscilloscope, and if you look down the bottom here, we can see the frequency is 1.844 megahertz. I'm also just going to put the probe onto the board out pin on the chip as well, and we're just going to check to see what frequency is coming out of here. I need to change the scale a little. Now, in fact, when the chip is new, then the default frequency you get is quite a lot lower than this, but you can see here that in fact the frequency here is 153 kilohertz. Now that happens to be the correct frequency for producing 9600 board. So in fact, if you divided that by 16, you would actually get 9600 board. So the clocks look like they're okay. So what we're going to do now is to fire up the terminal program. So I'm just going to do a very simple test. First of all, we're just going to send the first 16 bytes of the EEPROM first of all. So we'll be looking at what appears on here. So we'll just now go into the monitor and we'll send the first 16 bytes of the monitor, and we'll see what comes up on the display here. Okay, so what we need to do is first of all we're going to send the extra segment to be F000. So this is the top area where the EEPROM is, and then we're just going to do save 9000, and the finish address is going to be 9010. So we'll just switch back to the terminal, and if I now press the 0, and we can see we've actually got something coming up here. Now this is in fact the SREC format, and what I'll do is we'll just do this again and I'll capture it this time. So what I'm going to do is to clear the screen, start over. Right, we'll just do that again. Okay, so that's finished. And if we have a look at the capture file that we've got here, so you can see that this S1 and S9 are part of the SREC file format. And if we save this as .srec file, then in fact Notepad++ is able to interpret these. And if we have a look, you can see there's actually some highlighting here. And what this actually shows us, I'll show you a slide of what the SREC format is, but there's a checksum on the end here. And if, for example, this value was E rather than F, then in fact it would show that the checksum was incorrect. If we change this back, and if we change the count of the number of bytes here, then again this would show us that the number of bytes of data there is incorrect. So the SREC format is fairly straightforward and simple, but it does allow us to check that the data that we're sending is actually okay. So if we just have a look at the slides, this is a slide I've got on the SREC S19 record format. This is just from Wikipedia, so if you search for SREC S19, and the key thing is here, there's lots of different record types it supports for different sizes of data, but the ones that we use is the S1 record type, which basically is for 16-bit address and byte data, and then the S9 record is what the monitor looks for the end of the file, and so the S9 just says this is the end of the file. And there are checksums, and the way how the checksums are calculated is based on the calculations here. And the LED display on the monitor shows F for finished, C if there's a checksum error, and E if there's a hexadecimal conversion error. So if we had an invalid hexadecimal value, then that would get E on there. Now, I'm not going to test that for the moment because I've tested that in the first series on this, so I know that that side of things works. So the main thing we're interested in is the serial communications working. So I'm just going to show you the problems that I had with the reset and how I fixed that. So one of the reasons for this delay in getting this video out is that this problem has caused quite a bit of trouble. So it was actually caused by the reset active high reset line as opposed to the active low reset line having interference on it and actually causing the UART problems. In particular, was causing the UART to reset up to 2000 times a second, which is never going to be good. So this is the output of the oscilloscope of the probe grounded near where the reset line is on the UART chip. This is actually the oscilloscope probe on the reset line when it's supposed to be low, when there isn't supposed to be any active reset. Now, the trigger on this was actually set at 2 volts, which is the TTL minimum high value. So any value over 2 volts is interpreted as a TTL high value. And you can see here with 1 volt per division, so the baseline value here, this is 0 volts, 1 volt, 2 volt, 3 volt, 4 volt, 5, so 5 volts is up here somewhere. And what you can see here is there are a number of instances here when we're looking at 20 microseconds per division where the spikes on here are actually going above the TTL minimum high level. If I look at look over a slightly longer time here of 500 microseconds per division, then we can see that in fact these spikes are occurring above the 2 volt level at quite regular intervals, and it's about 2 kilohertz, 2000 times a second. This was obviously causing trouble, and what I did was I was checking the register values on and outputting these on the logic analyzer, and from time to time they were getting zeroed for some reason, and this was changing the UART from using 8 bits no parity to 5 bits no parity, which certainly messed things up a bit. And this is the high value, so you can see that this is the 0 volts here, and this is the high value. And what I ended up doing is, all I've done is reused one of the unused pins on the decoder PLD, and all I'm doing is taking the active low reset signal and inverting it, in fact, for use on the local board here. And it seems that the active low signal doesn't seem to suffer from the same interference issues that the active high one does. And so this is now what the reset looks like. So I've called it X reset. And so this is the same parameters as we had on the one showing the repeating spikes there. And in fact, if I then toggle it between the reset we've got now versus what it was, you'll see that it's really quite a big difference. So these are just one of the sort of things, particularly the strip board bus seems to be picking up a certain amount of interference. So it's something I'll need to look into. But by fixing that, then the thing has now actually running fairly reliably. And the other test I was just going to do is I've got one of the test programs that I was using some of the earlier videos. The LED key test version 3 was the one that I used in some of the earlier videos where we're getting the display and the keypad to work. And all I've done is I've updated this slightly so that I can load it into the memory at about 7000 segment. And I've just modified it slightly so that it will run in that area, won't interfere with the monitor. And all this is doing is putting nanocomp on the display, showing some values for testing out these 2 left segment, right segment routines. And then what it will then do is to highlight the key code for each of the keys that it pressed. So I just wanted something that I could output down the serial port just to make sure that everything was working okay. And when we assemble this, you'll see here the file type here is SREC rather than binary. So for EEPROM we normally use binary, but for the serial port we'll use SREC, and the SREC file for this particular program is here. So you'll see here if you look on each line, data bytes here, that's 64, so there's about 32 bytes of data here. We've got our S1, the number of bytes on the line, the address that it's going to be loaded at, that's 4 hexadecimal digits for the address. Then in this case we've got 32 hexadecimal bytes here, and then we've got the checksum on the end. And then at the end we've got our S9, which basically says this is the end of the file. So all you need to do here is to copy this onto the clipboard. All I'm going to do is to use the real-term send function here. So you can see we can just send a file. So I'm just going to go down onto the nanocomp and we'll go into load. So that's the finish. So all we need to do now is we're going to set the extra segment to 700, and we'll also set the code segment to 700 as well. So when we come to run it, it should run okay. So now I'm going to hit load, and so it'll just sit there waiting for me to send the file. So I'll just send the file, and that has finished. That's okay. And all I'm going to do is just do go 0000. We've got nanocomp. We've got the test pattern. We've got our 89 to F, another test pattern. And now if I press the buttons, it will show the key code. So you'll see the key code sort of go across the keypad. So that indicates that the download is working. The saving appears to be working. I'm going to do some more testing on it, but it looks like those side of things are working okay. So I've got the serial port working, though the reset issue did take quite a while to resolve, and it's only after I put the oscilloscope on some of the lines that I saw these spikes and things. So it's always worthwhile having something like an oscilloscope. You don't need to use it all the time, but there are those occasions where everything else has failed that the oscilloscope actually picked up a particular problem. So that's all I was going to do for this video. So we've now completed our nanocomp 8088. So we now have everything on the left-hand side here working. We're able to use a serial port using a PC compatible serial port, and the SREC file for the loading and saving is working as well. In the next series of videos, we're going to be looking at what makes a computer IBM PC compatible, which we've looked at in the previous series. And in particular, we're going to be looking at adding the power on self-test port and some of the port B, which is used to configure things like the faster clock speed turbo mode. And then we'll be building out the interrupt controller, speaker timer, real-time clock, and getting the BIOS up and running. And the reasons having these things at the top here is that the BIOS goes through and initializes all of these things at the beginning. And so if we don't have these set up, then the BIOS won't really be able to get any further. And then we're going to be looking at building out the text modes of the CGA video controller, getting a PS2 keyboard controller as well, the floppy disk controller, and then hopefully we'll then be able to boot MS-DOS from the floppy disk. And then after that, we'll be looking at adding hard disks, booting MS-DOS from hard disks, adding all of the graphics modes to the CGA video controller, adding a mouse, and then running Windows 1, 2, and 3 like we did in the first series. So thanks for watching. If you don't want to miss out on future videos, then please hit subscribe, and if you hit like as well, it just helps to make the videos available to more people.